Hi, my name is Елена Lulina, and I am a researcher at JetBrains Research. I would like to present to you our Task Tracker tool, a toolkit for tracking of code snapshots and activity data during solution of programming tasks. With an ever-increasing presence of software in our lives, programming education also becomes more and more popular. However, teaching programming is challenging. The understanding of students' programming behavior can be a valuable source of insight into the learning process. For example, there are several studies that try to indicate gaps in students' understanding or detect typical errors, which can facilitate the process of teaching. The other works aim to reveal code patterns common for novices, which may help to improve programming tools for beginners. To do all these researches, one needs data containing interaction between a student and their programming environment. Such data may include sequential code snapshots, compilation events, or actions performed in the integrated development environment. And to get such data, we need to have data collection tools. There are tools suitable for collecting data of interaction between students and IDE, such as CLion, Marmoset, DefEvent, or Blackbox. Usually, they are implemented as plugins for IDEs and tend to have client-server architecture to facilitate data gathering. Although the existing tools provide wide opportunities for data collection and analysis, they also have several restrictions. Being the IDE plugins, they are suitable only for the users of these IDEs and are restricted to a limited audience or even a particular programming language. Many features that are sometimes included in tools like chats or code review, while providing additional value, make the tools less flexible and harder to integrate into an already established teaching workflow. Also, some of the tools don't collect student snapshots of code or take them too rarely to restore the solution's timeline. Moreover, information about the task that the student is currently working on is not always complete. Such information can be essential to analyze the process of programming, which causes most of the difficulties for students and therefore is interesting to study deeply. In our work, we strive to overcome the restrictions of the existing tools and present a tool called Task Tracker. To extend the user's audience, it is designed as a plugin for IntelliJ-based IDEs, such as IntelliJ IDEA, PyCharm, and CLion, and therefore supports working with various programming languages, such as Java, Kotlin, Python, and C++. This tool collects snapshots of every code change and user actions together with the information about currently solving tasks. Similar to other tools, Task Tracker tool has client-server architecture. It consists of a plugin for IntelliJ-based IDEs that tracks all code changes and works together with the Activity Tracker plugin that tracks actions, a server, and a separated post-processing tool. We also present a public dataset of problem-solving activity data of 148 students retrieved and analyzed with Task Tracker tool. The goal of the Task Tracker plugin is to collect all consecutive code changes and IDE actions during the solution of a programming task. Its user interface allows a student to fill a survey with such fields as age and programming experience, choose a task to solve, and view the task description right within the IDE so that the student is not distracted from the solution process if they have to consult with the description. The plugin works in conjunction with the Activity Tracker plugin that captures students' interaction with the IDE, such as copy-paste, run debug, and other actions. Task Tracker plugin is designed to collect only task-related data, so it automatically creates files for each task where the user should write a solution and tracks changes only in these files, protecting the user's privacy. It takes snapshots of every code change and stores them in comma-separated values format. The installation of the plugin is simple enough to be performed even by inexperienced users. All the user should do is to install the plugin from disk within the IDE. After the IDE restart, it connects with the server and receives all the necessary data to initialize its UI, such as a list of tasks or UI languages. Currently, our plugin supports two UI languages, English and Russian, but additional languages can be easily added on the server. The first panel contains a survey with age, country, gender, and programming experience. All the field data is stored locally, so it's not needed to be filled every time. Next, the user can choose the task from the given list and view its description and correct examples of input and output. Then, the file for writing a solution is opened, where the user can write their code. After completing the solution, the user can submit it and choose the new task. Besides collecting data remotely and storing all data in one place, the server is in charge of configuration of the plugin's UI and allows users to customize pretty much everything: the UI language, the survey, and tasks with their descriptions. All you need to do is to change the configuration file. Information that is common for all the languages, for example, inputs and outputs for tasks, is filled only once. Otherwise, it should be filled for each language, like it happens to task descriptions. The server could be launched locally or remotely, depending on the desired setup. To do so, you need to start it using Node Package Manager by running npm start command from the server folder. If you start the server for the first time, you also need to generate a database with information about tasks and the survey. Sending the post query to the server will do it for you, and after receiving the positive response, you may use the server together with the plugin. It is also very easy to download all the collected data from the server. All you need to do is to send a GET query to the server and download the data from the received path. All data is split by users and tasks and contains task tracker and activity tracker files. The purpose of the post-processing tool is processing, analysis, and visualization of the received data. It's designed as a separate tool to minimize the size of the plugin, perform time-consuming operations, and allow users to choose the preferable post-processing procedures. The task tracker files contain several columns, such as date and time, file name, current fragment of code, the survey information, for example, age, and so on. One of the post-processing steps is merging of task tracker and activity tracker files, since they are coming from different plugins. For each action, we need to find the fragment it was performed on and merge them into one file. Besides that, you can score the solutions to detect correct ones if you add the input and output files for this task. It is done by running the tests and counting the rate of the past tests. Since the data collected by the plugin contains every code change, one may not necessarily need such fine-grained data, so it can be filtered. For example, by removing all intermediate changes that happened on the same line. The analysis of the received data can be done using a visualization model of the post-processing tool. For example, various statistics of tasks, languages, age, and program experience can be shown on interactive plots. These three parts, the plugin, the server, and the post-processing tool, form the task tracker tool that suits several needs for both teachers in programming courses and researchers in data gathering. First, thanks to remote configuration capabilities, it can serve as a framework for the observed problem-solving in the classroom. In addition to that, analysis of the gathered data within the course group can help improve the course by tailoring the curriculum to adjust the difficulty of tasks or letting the teacher focus on topics that the students may find hard. Moreover, during data gathering, students have an option to disclose their identifiers to the teacher. This allows to build a personalized overview of the solution data for each student and provide individual insights. While the same result can be achieved by talking to students, conversations with each of them may take more time and the teacher's energy compared to the monitoring of the visualized solution process. Finally, the plugin can help identify cheating. For example, if a large piece of code was inserted after executing the pass command, which miraculously leads to a perfect score, the teacher may want to be more attentive. Such events can easily be highlighted in data collected by Task Tracker tool. Besides the classroom use, Task Tracker tool can be used to collect data in a wide variety of research settings. The primary characteristic that makes it suitable for research data gathering is flexibility. Task Tracker tool has a client-server architecture which enables remote data gathering. Moreover, UI text and tasks can be configured in any language, which doesn't limit the collection of data only to English-speaking participants. The plugin is easy to install into the IDE. In addition, we provide detailed step-by-step guides for installing and uninstalling the plugin. Our own experience with using Task Tracker tool for data collection demonstrates that even users with little programming experience are able to install and set up Task Tracker plugin easily. Task Tracker tool is designed with care for users' privacy. The data is sent anonymously, and the check-in feature only extends to files automatically created by Task Tracker plugin. This ensures that users' privacy is respected and protects their personal data from being unintentionally fingerprinted during data collection. We used Task Tracker tool to collect a dataset of problem-solving activity data. We chose 6 tasks of different difficulty levels, the easiest of which was to count the cost of n pies given the cost of 1 pie, and the hardest one was to place the brackets in the right order. We had 148 participants aged from 11 to 40 with the mean age of 19 years taking part in the data gathering process. Their programming experience range is spanning from 0 to more than 6 years of programming, but sometimes users set different experiences during the session, which we consider as incorrect. During data gathering, solutions were accepted in one of 4 languages: Python, Java, Kotlin, or C++. The total number of submitted solutions is 474, with only 326 of them being correct. Each solution represents the whole programming process, with all code changes and actions performed. Since code may contain personal information, all comments were removed, and all names of variables, functions, and so on were anonymized using our anonymization tool. The resulting dataset is open to use. We analyzed the collected data and used the post-processing tool to explore the dynamic of the solution score. We removed all intermediate code changes and colored each code fragment according to its score. The plot shows that after getting the correct solution with the highest score, the student continues to edit it, even reducing the solution score. Given their code, we can find that these actions were code refactoring. This approach allows to reason about students' intent in detail, together with releasing common behavioral patterns. Using another visualization type of post-processing tool, we plotted run and past actions together with the length of the current code fragment. At the beginning of the solution, the user passed a large piece of code, which turned out to be the keyboard input code from a previous solution. Further, the user took a break for about 6 minutes, which we can explain as the moment of reflection. Another interesting detail is an abundance of code runs, which is quite unusual for most users. Also, we found that in the middle of the process, the user passed actual and expected outputs of their program for character-by-character comparison, thus using the editor as a div tool. The collected dataset can be used in many studies. For example, to investigate the correlation between programming experience or age and the use of language features. Also, it would be interesting to see the most frequent changes and IDEA actions after achieving a perfect score. A deeper study of common errors for different experience groups could be another potential application of our dataset, together with the implementation of advanced solution metrics, such as a total count of characters added or removed during the solution, or time spent on writing code. Finally, changes of code can be used to build a model of the solution process of a given task and suggest personalized hints to help students make the next step to the correct solution. This application of the dataset we use in our ongoing research project. In this presentation, we introduced Task Tracker tool, a toolkit for collecting exhaustive code snapshots and user actions during the solution of programming tasks. The toolkit enables its users to gather task-specific data of solution activity, collect it on a server, and perform basic analysis over it. Using the toolkit, we collected a dataset of solution activity of 148 participants with different experience levels. The dataset is publicly available. We found several interesting patterns in the dataset and suggested multiple directions for future use of the dataset and our toolkit. Here you can find all the links to the source code of the implemented tools. If you have any questions, feel free to contact me at the given email. And thank you very much.